Okay, so good afternoon, almost evening everyone. So let's begin. Right, so the next main goal, let's just do a quick recap of what we have done so far. We have proved a few major results. The first important result we proved was the canonical partition theorem, which says that for any matching code graph, the maximal barriers partition its vertex set. In the grand scheme of things, the proof was not too difficult. At least after the other things you have covered since then. And then we saw a proof of Lovász's unique tight cut decomposition theorem, right? That every matching code graph, if you apply the tight cut decomposition procedure, you'll get a unique list of bricks and braces up to multiplicities of edges, right? And after that, we also proved one more very interesting result, which explained the subadditivity of the B function. If G is a matching code graph that is obtained by splicing two matching code graphs G1 and G2, then B of G is less than equal to B of G1 plus B of G2, and equality holds if and only if the splicing is a tight splicing. We phrased it in terms of separating cuts, but of course separating cuts is the same as splicing two matching code graphs, right? So those are the three main results we have seen so far. Okay, and of course your assignment has several interesting results, and your assignment 5 of SGT had some interesting results, including the ear decomposition theorem for bipartite matching code graphs. Right, so all those are also there. Anyways, we are now done with the first 4 chapters of the book. We are now on chapter 5, which is called characterizing bricks and braces, or characterizations of bricks and braces. So the main result of this chapter is the ELP theorem, Edmonds, Lovász and Pulleyblank. They proved that every matching code graph that has a non-trivial tight cut has one that is either a barrier cut or a suppression cut. Yeah. No, it's not that difficult. You can take off the helmet. Yeah. So that's what we'll prove. We will prove that there is an ELP cut. So by ELP cut, what I mean is a non-trivial tight cut that is either a barrier cut or a suppression cut. Yeah. I think Lucchesi Murty probably don't require it to be non-trivial, but that means I have to always say non-trivial ELP cut. That's annoying, so I'm going to put non-trivial in the definition. Of course, I don't need this for two suppression cut. Two suppression cuts are by definition non-trivial, but barrier cuts are of course for trivial cuts. All trivial cuts are barrier cuts. Yeah. So, all right. So this is what the result says. There is always an ELP cut once your graph has a non-trivial tight cut. In other words, every matching code graph that is neither a brick nor a brace has an ELP cut. And please convince yourselves, if you haven't already done it, it was a DIY or a DIY in a previous lecture, this result is equivalent to this result. Bricks are precisely the 3 connected bicritical graphs. There are 2 things here. Bricks are 3 connected bicritical, and 3 connected bicritical means bricks. That's what precisely here stands for. Right? So this gives you a characterization of bricks, an alternative way of defining bricks. In fact, historically, this is how bricks used to be defined in the 1980s and 70s. People used to define bricks as 3 connected bicritical graphs. It is only later that we realized, because of ELP 82, that oh, these are exactly the non-bipartite matching code graphs that do not have non-trivial tight cuts, which is today the standard definition of bricks. Yeah. Okay. So this is what we want to prove. Theorem 5.6, ELP theorem. Some context I want to give you here is the original proof in 1982 by ELP used LP duality. linear programming duality. If you have never seen linear programs, or if you haven't seen duality in particular, don't worry, you will probably see it eventually in some course. This is how they proved it. So it was not in particular a graph theoretical proof. It relied on techniques that are not generally considered to be graph theoretical techniques. This was in 82. In 2002, Zoltán Szigeti visited Waterloo when I was doing my PhD there. We had some nice time together. So Zoltán gave a graph theoretical proof. This was the first graph theoretical proof. And since then there have been more graph theoretical proofs, mainly one by CLM. I forget the year in which it was published. Probably it is a 2018 paper, I think. But the year of publication is not necessarily the year of proving. So they gave another graph theoretical proof that is inspired by some of Szigeti's ideas. Although I would argue that's probably simpler, and in some sense you don't have to go that much outside the theory of matching code graphs. You still have to, a little bit. You have to go to matchable graphs in particular at some point. But anyways, in the grand scheme of things, I personally think that the CLM proof is even simpler than that by Zoltán. And the one that is in Lucchesi Murty is probably an even simplified version of the CLM 2018 proof. So the proof we are going to see, I want you to see that it's a long time since 1982. The proof we are going to see is from the book published in 2024. That's nearly 14 years. Yeah? More than 40 years. And in the span of 40 years, the proof has been simplified a lot. That still doesn't mean it is the simplest proof out there. Maybe some of you will simplify it further, I don't know. Right? So that's how things are. Questions, concerns? Yeah? Okay, I want to briefly mention a stronger result than ELP theorem, which we will not prove in this course. So this result is simply saying that if there is a non-trivial tight cut, let's say C, then there is also an ELP cut, D. Of course, C could be equal to D. Maybe the cut I give you is already an ELP cut, then there is nothing to prove. That's one way to think about it. If I tell you that there is a non-trivial tight cut C in the graph, then there is also an ELP cut, say D. The two cuts C and D could be crossing, they could be laminar. The laminar ELP conjecture, conjectured by Carvalho, Lucchesi Murty, although I think the main person behind the laminar ELP conjecture might have been Claudio Lucchesi, says that, well, you can guess what it says. The laminar ELP conjecture says that given any non-trivial tight cut in a matching code graph, say C, there is an ELP cut D such that C and D are laminar. No longer a conjecture. I forget the names of all the authors, but I know Claudio Lucchesi is one of the authors. It says that, so G is a matching covered graph, C is a non-trivial tight cut in G. Then the theorem says there exists an ELP cut D such that C and D are laminar. Proof of this is not even included in the Lucchesi Murty book. So it's a published paper from when I was a postdoc, so must be 2019 or 20 maybe. And of course the published paper has a proof of this, but they did not include a proof of this result in the book. They give some sketch, they give some ideas that okay, these are some ideas and concepts that are used in the proof, but the proof is too lengthy, so they decided to just omit it from the book. You want to read it, you go read the published paper. Yeah. So, yeah. Anyways, I'll probably tell you the authors later. I don't remember the authors. But we will not see a proof of this. We will see a proof of this. Yeah. In most cases, most applications of this theorem, you can of course apply the stronger result, and the application's proof becomes shorter because you don't have to consider the crossing case anymore. You can assume that they are laminar because of the stronger result. But typically, I don't know of any applications of this result that cannot be proved using this result. That just means that we are not there yet. Any questions, concerns regarding the two statements? Okay, and now let us also appreciate one fact which we have seen before. In general, of course, a tight cut need not be an ELP cut. A non-trivial tight cut need not be an ELP cut. The standard example in the literature and also in the book is this one. This is a non-trivial tight cut, and this is not an ELP cut. In particular, you can check that this graph is bicritical. That's not too difficult to check. You can delete any two vertices, remaining graph is a perfect matching. So therefore, it can't have a non-trivial barrier cut. So the only possibility for an ELP cut is a two separation cut. The only two separations in this graph are U and V and U and W. And if you consider either of them, you will not get this cut. You will not get the cut C. Right? You all agree? Okay. That being said, of course, because the ELP theorem holds, there are cuts that are ELP cuts. Well, there is a two separation. So let's draw all the two separation cuts. There are two separations, and there are only two components. So we will get exactly 4 cuts. Let's draw all the 4 cuts. If I take this two separation, I get this cut, and I take this and V, and I get this cut. Those are the two separation cuts we get from the two separation UV. And now let's do UW. UW, we get this cut, and we get this cut. We got 4 cuts. If I am not mistaken, these are the only 5 non-trivial tight cuts in this graph. I did not check this, you can check it later. One of them, C, is not an ELP cut. The remaining 4 I have drawn here are ELP cuts, of course. They are all two separation cuts. And you can see that there are some that cross the original cut. 2 of them are crossing C. The other 2 are actually laminar with C. The ELP theorem says that there is an ELP cut. Given any non-trivial tight cut, there is an ELP cut. They could be crossing. This one says there is actually a laminar one. Yeah. Okay. Questions, concerns? We will not prove the result today. I am yet to do my own homework to prove it. What we will do is we will discuss the ingredients and try to prove all of the ingredients that will be required in the proof, which we will hopefully complete on Thursday itself. The entire proof of the ELP theorem, right? Okay. Any questions or concerns regarding what we've discussed so far?
non-trivial tight cut, but it is not two separation.
C is a non-trivial tight cut, but it is not a two separation cut. Yeah. In fact, let me write that.
And also a barrier cut.
It is neither not a barrier cut also. Yeah. This is a bicritical graph, so there are no non-trivial barriers. Yeah. So this is a non-trivial tight cut that is not yeah. And one of the questions that I asked you all earlier, this is a 5 cut C. Can you find an example of a 4 cut that is non-trivial tight cut but is not an ELP cut? I don't know. I have not tried it, but maybe one of you will try it and figure it out. Yeah. Of course, 3 cuts will not work because you already proved that 3 cuts are barrier cuts. In any matching code graph, if you have a tight 3 cut, then it is a barrier cut. By the way, I forgot to mention the proof that we saw for this result, tight 3 cut is a barrier cut. Srijit, who is not here, had a different way of completing it, and he made a DIY or TIY out of it. You can check it out. So it's more or less the same thing, but the way he completed the argument is actually different in a sense. He actually uses a pigeonhole principle and finishes the proof in a nice way. He made a DIY or TIY on Piazza. You can check it. Yeah. It should say PHP. Yeah. Okay. Good. Questions, concerns? All good? Yeah? Okay. So let's go back to this. How would you prove such a result? Okay, let's assume we know the result. I mean, we do know it is a correct result. So how would you prove such a result? You know that the graph is a non-trivial tight cut, but that tight cut could look crazy. In fact, I want to comment one more thing here actually. In some sense, you can say that we don't have a complete characterization of tight cuts. This result is not a characterization of tight cuts. It doesn't tell you what every non-trivial tight cut looks like. It tells you if there is a non-trivial tight cut, then there is a nice one, a barrier cut or a two separation cut. It doesn't tell you the structure in some sense of every non-trivial tight cut. You all see that? Yeah. This result, however, in a certain sense, this can be viewed as a characterization of tight cuts. Let me explain. This is how Claudio Lucchesi likes to explain it. Take any non-trivial tight cut. Let's make a drawing. Supposing I have a matching code graph G and I give you a non-trivial tight cut C. If this is an ELP cut, well done, nothing to do. But if it is not an ELP cut, then let us apply the laminar ELP theorem. Then by the laminar ELP theorem, there is another non-trivial tight cut that is laminar with the given one. Again, this may also not be an ELP cut. Oh, this is actually ELP cut. Yeah, this is ELP cut. Good. So what I can do is, now I can shrink this shore into a single vertex. So let me give labels. Supposing this is X, this is X bar, I don't know, this is Y, this is Y bar. What I can now do, I can shrink this shore into a single vertex. And now C is again a non-trivial tight cut in the smaller graph. If it is laminar in the smaller graph, good. If it is not laminar, again apply this theorem. Now in the smaller graph there is a non-trivial tight cut, that is an ELP cut, and that is laminar with the given graph, with the given cut C, in the smaller graph. So that will look like, if you go back to the original graph, that cut will look like this maybe, or it could be here somewhere. Right? You get a smaller graph, again this is a non-trivial tight cut. Now it may be laminar ELP cut in the smaller graph. If it is not, again apply the theorem. Ultimately you will get a matching code graph in which this cut will still survive, and it will be a laminar cut in that graph. It will be an ELP cut in that graph, because it's a finite number of steps you have to stop, right? You see the point? So if the cut is not ELP, then you take a laminar cut that is ELP, and you consider a contraction in which this cut survives. Now if it is ELP, stop. Otherwise again you take a laminar ELP cut. Eventually you will get a matching code graph in which the original non-trivial tight cut is still a non-trivial tight cut, and it is an ELP cut. So in that sense, every non-trivial tight cut is ultimately an ELP cut. Let's do the second example. This is not an ELP cut. Yeah? But according to the theorem, the laminar ELP theorem, there is a cut that is laminar with it. That is an ELP cut. So what I will do is now I will shrink this into single vertex. Let's do it. So what will I get? When I shrink this, so this is my C and this is my D. That is laminar with C. Yeah? And now let's shrink this side into single vertex. This is okay. And now I have to draw this vertex. And how many edges? 2 edges going to this vertex. 1 edge going to this vertex. 1 here and 1 here. And let's draw the original cut C. This is the original cut C in this D contraction. Now is it an ELP cut in this graph? In this graph, is it an ELP cut? Yeah? Right? It is, I think. U and I don't know, maybe X and Y. Right? So in the smaller graph, it is an ELP cut. So that is why Claudio likes to call this the ultimately ELP cut conjecture. Now a theorem. Ultimately. Right? So that's one way to look at it. So in some sense you can think of this as a complete characterization of tight cuts. But we will not prove this result. Okay, so let's go back to the earlier thread. So how do we prove such a result? Right? If you want to prove this kind of a result in life, how do you go about it? What is some very abstract way of going about such a thing, such a result?
Suppose this is not a barrier cut, prove it is a two separation cut. Otherwise,
yes. So, but the thing is, the cut I give you, that may actually not be barrier cut or a two separation cut. Right? You have to show the existence of one. Like I give you this cut C. It is neither barrier cut nor two separation cut. So you won't be able to contradict that because there are such cuts.
So I am saying the existence that suppose that they are not existing.
Supposing there is no such cut at all.
Yeah, non-trivial barrier. Then so that there exists.
Supposing there is no non-trivial barrier cut, then you try to show that there is a non-trivial two separation cut. Yeah. Okay. That's one way to go about it. In fact, this is relevant to the proof. In the proof, in some sense, let me see, if the graph is not bicritical, then we can actually finish the proof easily, I think. And then the difficult part is the bicritical graphs. There is no barrier cut in those graphs. And you have to show that there is a two separation cut. So actually we will do something like that in the proof. Yeah. Okay, any other thoughts, any other ideas? Sorry? Induction.
We have a non-trivial tight cut. We have a very natural way of going to a smaller graph and we'll show that there is but that might not be an ELP cut in the original graph.
Right. And in fact, what could happen is both the contractions might be bricks or braces. Well, in that case, probably it's not too difficult. Then you just have to consider splicings of bricks and braces. Well, braces are easy because they're bipartite. So, but yeah, so then probably the difficult case will be when at least one of the two contractions is actually neither a brick nor a brace. And so in the smaller graph, there is a non-trivial tight cut.
So if it is a brace, then we are somewhat done because then there exists a barrier.
That's right. If you have a shore that is bipartite, then you're actually done. Then there's barrier cut. So actually, that is how you actually get rid of bicritical graphs that are not bicritical. That's basically how you get rid of that case in some sense. Okay, any other thoughts? Any other ideas?
You start with the three-connected bicritical graph and a non-trivial tight cut and arrive at a contradiction to the tightness or something.
Yes, you are basically trying to prove this result. You are saying that you look at this equivalent result and you try to. So we know that bricks have to be three connected and bicritical. That is actually the easy direction. What is not immediate is that three connected and bicritical implies brick. That is the harder part. So what you are suggesting is take a three connected bicritical graph and show that there is no non-trivial non-trivial tight cut. Right. Okay. Any other thoughts? So here is another thing we often do. We have seen several proofs like this in SGT. You want to show that an ELP cut exists. What you know is that a non-trivial tight cut exists. ELP cut is a special type of non-trivial tight cut. So what you do is you try to maximize or minimize something. You try to optimize something. You say I will choose a non-trivial tight cut with blah 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 property, typically some kind of optimization. I don't know what to optimize. And then you say that hey, because I chose it like this, it actually works. Yeah? This is one way to do. It won't work actually. So the particular optimization I'm going to propose, which is what Carvalho and Lucchesi Murty discuss, it doesn't really work, but it sort of does. That is why we need theory. Okay. So so let's talk about special type of non-trivial tight cuts. Supposing this is a non-trivial tight cut. So there are two contractions. There are two C contractions. If either C contraction is a brick or a brace, what does that mean in this graph? Supposing one of the C contractions is a brick or a brace. What does that tell you about tight cuts in this graph? I tell you that one of the C contractions is a brick or a brace. Let's suppose G shrink X bar is a brick or a brace. When I shrink this into single vertex, I get a brick or a brace. What does that tell you about the other tight cuts in this graph? They are all laminar to C, but can you make it stronger? Huh?
Will be tight cuts of G1, that is contraction, when contracting the brick or the brace.
Right. You mean the other shore? Yes. Where? Right. So if I shrink this and I get a brick or a brace, that means all other non-trivial tight cuts in this graph, they look like this, not like this. All other tight cuts, the laminar ones, I will be drawing them on the right side of this. Okay? Okay. Another way to think of it is, we have minimized this shore with the property that the cut is tight cut. I'll write the definition in two different ways. So convince yourself that the following are the same. We will call these peripheral tight cuts. Okay, so here are two definitions, they are equivalent. It is a non-trivial tight cut such that one of the two contractions, at least one of the two contractions, is a brick or a brace. A non-trivial tight cut, C, such that at least one of the two C contractions is brick or brace. Another way to define it is a non-trivial tight cut. I'm going to minimize x. C colon equal to partial of x such that no proper subset for all non-empty x prime subset of x, proper subset of x, partial of x prime is not tight. We have chosen a non-trivial tight cut such that one of the two shores is minimized. So if I minimize the x shore such that the partial x is a non-trivial tight cut, that means that any proper subset of x, non-empty proper subset, that should not give me a tight cut. If I do that, that simply means that when I shrink the complement of x, I have a brick or a brace. Yeah, do you all agree that they are equivalent? Sorry? Non-trivial tight cut such that partial x, I didn't get it.
Partial x dash be a non-trivial. It's not a
No. Oh, I see. Yeah. I don't want singleton. Is yeah. Actually, let me make it this. Let me make it. Is that okay? Yeah. Okay. So if I take any, I don't just want non-empty subsets. I want non-singleton subsets. So yeah, therefore I can make it at least 3. That works. Yeah. Thank you. Good. Yeah. Everybody agrees these are equivalent? Yeah? Good, thanks. Okay, so these are called peripheral tight cuts. So it is intuitive to try this at least. If you are trying to prove such a result, I mean, you would try something like this. Let me take a peripheral tight cut and let me prove that peripheral tight cut is ELP cut. That would be fantastic, right? But there is a problem. You all see the problem? C is a peripheral tight cut. It's not an ELP cut. Right? One contraction is K4 with multiple edges. Brick. Yeah? So it doesn't work. But in some sense it does. In the sense that although the peripheral tight cut won't work, something in the vicinity of that peripheral tight cut actually works. And that is sort of my current understanding of the CLM proof of the ELP theorem. And hopefully it will improve as I read further. But I'm still trying to figure out how they prove it. Right? So they use peripheral cuts actually. Ideally what you would like to prove is any peripheral cut is an ELP cut. That's a false statement. But they prove something else about peripheral cuts. So one of the results is a property of peripheral cuts that will be used in the proof. Okay? Fine. So let me state that property. This is lemma 5.1. So if you take a tight cut partial of x in a matching chord graph G, what can you say about the graphs induced by x and x bar? What is something you can say about these graphs? The graphs on odd number of vertices, clearly. Do we know some basic property of tight cuts? Connected. They're bonds. In fact, separating cuts are also bonds. Okay? So the graph induced by x and the graph induced by x bar, of course, they are connected. This property says that something stronger is true. In the cut, there is an edge uv. U is in x, v is in x bar. So that the graph induced by x minus u and the graph induced by x bar minus v, they are also connected. Okay, that's what the property states. So property is G is a matching covered graph. C partial x is a peripheral tight cut. Then the result says there exists an edge E uv in this cut C such that adjust notation u is an x, v is an x bar, but more importantly G induced by x minus u and G induced by x bar minus v are both connected. Yeah, statement clear? Let's look at an example which demonstrates peripheral is crucial. Yeah. Maybe I'll erase some of this. I don't need this anymore. Well, let me keep it for now. Where is this? This is the smallest example of a two separation cut. It is also the smallest bicritical graph that is not a brick. We will generalize this example. Here's a matching chord graph, not too difficult to convince yourself. It's very symmetric. And I claim that in this matching chord graph, you can find a tight cut that doesn't have this property. There is a tight cut in this matching chord graph such that for no edge in the cut, you can say that the graph induced by x minus the end of the edge and the graph induced by x bar minus the end of the edge are both connected. Can you all try to find such a cut here? If you have found it, let me know and I'll come and talk to you. Yeah.
These two and this one.
Yeah. I'll give you a hint. It's a two separation cut. The peripheral cut, not the peripheral cut, the non-peripheral cut you're looking for is a two separation cut. And there are only so many two separation cuts in this graph because there are only so many two separations in this graph. Right. See if you can choose a two separation cut that doesn't have this property. For any edge you choose in the cut, both these graphs cannot be connected. In fact, if I'm not mistaken, in this example, neither of them is connected. Is that correct? No, that's not true. That's not true. Yeah, one of them is not connected. Yeah, found it, everybody? Yeah? Found it? Yeah? Right, so you have to basically consider this. Observe that any edge you choose in this cut, it's either incident at U or it is incident at V. Every edge in this cut is either incident at U or at V. So therefore, one of the ends you will choose will be U or V, right? But if you delete U here, you have a disconnected graph. If you delete V here, you have a disconnected graph. Yeah? You can add one more edge to this graph and still the same thing happens. You can add an edge joining U and V. This is also matching covered. And still, even for this edge, well, this edge is even worse. Both the graphs will be disconnected. Yeah? So therefore, if your cut is not peripheral, then definitely this statement is not true. You really need peripheral in the hypothesis. Okay? But of course, what would have been really nice is to say that peripheral cut is an ELP cut. That's not true. But it has some nice property. It has this property that there is an edge with this additional property. You delete the corresponding end from each shore, the graph is still connected. Okay? Fine. So what? What to do? Okay? Alright. So this is one thing we will prove in order to prove the ELP theorem. It's not too difficult to prove actually. For now, if we don't finish it today, I will give it as a TIY. But we will prove it eventually. Yeah. Okay, good. So now I want to consider, so they are going to use this lemma and they are going to use this edge in particular, and then they have to still show the existence of an ELP cut. Yeah. So let's make a drawing of this situation, an abstract drawing, and try to understand what's going on. So this is my tight cut G in a matching code graph, non-trivial tight cut. Now you can forget that it is peripheral. I will just use this property. There is an edge. So there is some edge in this cut. Let's call this X. Let's call this X bar. And let me draw one edge. U is here, V is here. In the proof, what they will do is they will delete the ends of this edge. G minus U minus V. It's a bit tricky, right? I mean, it may not even give you a matching code graph. As I said in the WhatsApp message, we will deal with graphs that are not necessarily matching code. But is it matchable? Everybody agrees it is matchable. G minus U minus V is matchable. G minus U minus V is a matchable graph. This edge is the edge E. And you all agree that C minus E is a cut in G minus U minus V. C minus E, the set of edges C, delete the edge E, is a cut of G minus U minus V. Yeah?
There could be other edges coming
Yeah.
out of U.
Not true?
There could be other edges coming out of U and V.
Ah.
Whatever cut.
I see your point. You mean that there could be an edge like this. Yeah. Okay, let me not say this. Good point.
Subset of C minus C is
Yeah, let me just call it partial of X minus U. Partial of X minus U in the graph G minus U minus V. Yeah, maybe that is just, I did not want to use so much notation, but well, sometimes life doesn't leave you a choice. So let me use notation. So I'm basically still looking at the same partition of the vertex set, right? Yeah, so the same drawing kind of works. Delete the two vertices and now look at the same partition, X minus U on one side and X bar minus V on the other side. That is this cut. Partial of X minus U in the graph G minus U minus V. Okay? This is a matchable graph. What can you say about this cut? What can you say about this cut in this matchable graph? What can you say about the edges in this cut? Given that the original cut is a tight cut in the graph G. Right? So that is my question. Yeah, so just think about it. What can we say about edges of partial of partial of X minus U in G minus U minus V in the graph G minus U minus V. The graph is matchable and the original cut C was a tight cut in the graph G. So on the basis of this, can you say something matching theoretic about the edges of this cut in the graph G minus U minus V.
The type
Okay,
cut.
okay, I'll come and talk.
C also satisfies the property that this is star property or not? I think that initially you are saying that C satisfying this star property.
Yeah, so C satisfies this property in the graph G. Now my question is, I'm looking at the partial of x minus u in G minus u minus v. I know that G minus u minus v is matchable. My question is, what is the property of these edges? Property of the edges. I'm looking for a matching theoretic property of the edges, not a property of the cut itself. Yeah, yeah. It is not a positive property. Positive generally means belongs to perfect matching, is matchable. You're looking for a negative property. Sometimes we need negative. Yeah. Anybody else? Yeah. Right, so we are looking at the edges going from here to there after deleting these two vertices, right? Consider such an edge. Can it belong to a perfect matching of G minus U minus V? Given that the original cut C was a tight cut in G, right? You all see that it can't, right? After you delete U and V, you have an even number of vertices on this side and even number of that side. So if this edge belongs to a perfect matching, in particular you will have at least 2 in the perfect matching. Now you go to the original graph, now you have a perfect matching that meets the cut in 3 or more edges, contradiction to tight cut. So in fact we have an interesting situation. We have a matchable graph where there's a particular cut that does not have any edge that is matchable. All edges in this cut are unmatchable. Okay? That's what I'm looking for. Okay. Each edge in partial of x minus u in the graph G minus u minus v is unmatchable. In G minus u minus v. Okay? So we have a matchable graph. We have a particular cut in this graph. And all the edges that belong to that cut, they are actually unmatchable. Right? And notice that the two shores of this cut, they are actually connected graphs. The graph G minus U minus V itself may be disconnected. We don't know whether G minus U minus V is connected or not. But we know that the two shores are actually connected. Which means if there is a single edge in the cut, then actually the whole graph will be connected. But the cut itself could be empty. In which case this last statement is not saying anything because there are no edges in this. That's also possible. Yeah. So we will see a result on this situation. But it should not, yeah, I mean, I wanted to make sure that you see why this situation arises, right? We have this situation. The moment you apply this conclusion, right, and you delete these two ends, you will get this situation. So we will have a particular lemma that deals with this situation. Yeah? Okay. Okay. Notice that this statement, it's talking about two graphs being connected, right? And this one is about a matchable graph where a certain set of edges, they are all unmatchable. This is going to be somehow related to barriers, and this is slightly related to the connectedness of the graph. So that's sort of giving you some idea that it will eventually tie up with the ELP theorem. So we are going to use this result and some results about barriers, and then we are going to use all of that to prove the ELP theorem. But it's a pretty non-trivial proof. It is most likely the most non-trivial proof you have seen thus far. Right? Okay. So in the second part, I want to tell you results related to barriers. Okay? And one of those results will be in this setting. We will talk about special barriers that apply to this situation. But we are going to talk about matchable graphs, not necessarily matching covered graphs. This is the reason. We have deleted the two vertices u and v. Now we have a matchable graph. Need not be matching covered. Right? In fact, it is not matching covered. If there are any edges in that cut, then those edges are unmatchable. So it is not matching covered. If there are no edges in that cut, then it is a disconnected graph, therefore it is not matching covered. Actually, I did not realize this in the afternoon. Just realized now. Right? So G minus U minus V is definitely not matching covered. We just observed that. Either there are no edges in the cut after deleting U and V, which case it is a disconnected graph, or there are edges but they are unmatchable. So definitely it is not a matching covered graph. Yeah? Okay, good. Alright. So maybe we can take a break here. Maybe we can take some questions if there are any. And then after the break, we can go into some other results related to barriers. Given the time, I'm not sure if we will actually prove the ELP theorem this week. If we don't finish it this week, we will finish it on Monday. Yeah. Okay. Questions, concerns? All good so far? Yeah. Alright. So we'll meet again after the break. Thank you.